Right, so we're in the final section of this chapter on dynamics, and this is looking at forces and the link back to vector functions. And the cool thing here is that everything again looks at using F equals ma. So finding acceleration of the particle using F equals ma, and then we can actually find velocities, distances by integrating acceleration vector, and we can also find Cartesian equations by looking at the path of the particle in terms of vectors, so looking at the x vector function, and then looking at the components of the I and j, and then linking them back to a Cartesian equation, y as a function of x. So in this question, we first of all got part A, find the acceleration of the particle. Now we know the forces overall acting on this particle will be the addition of the two forces, F1 and F2. In this case, that's going to be 2 plus 3i, so 5i, and then 3j minus 4j, so negative j. We know that the mass, m, is 2 kilos, so m equals 2. And so now we can find a. So we know that 5i minus j equals the mass times the acceleration. So therefore our acceleration vector is going to be 5 over 2i, minus a half j. And that's because here we use F equals ma. This is our force F, this is m, this is a. So we've got our acceleration vector a. Now we're asked to find the position of the particle at time t, given that it is initially at this point. Okay, and we'd assume here it's a particle that's at rest. So that means that when initially we're looking at this particle being v equals 0. Okay, so we can first of all integrate here. We know that the velocity vector is going to be the integral of the I and j components. So 5 over 2, integrating with respect to t, I should write t equals 0 there. So it's going to be t I minus a half t j. Integrating with respect to t means that we just have these constants as coefficients of t. Plus we have a vector constant. Remember that when you integrate, you normally have a constant of integration. With vector functions, you have the constant, which is a vector. Now we know that v equals 0 when t equals 0 because we're initially at rest. And so that means that 0 is equal to c. So therefore, I've written that as 0 vector because that is a vector and it's equal to 0. So that means with no c, we have v. v is 5 over 2t I minus a half t j. Put a box around that one so I can see it. Alright, so the next part here we're looking at for part B, and I should label this as part B that we're doing, is we're trying to find the position of the particle. Now because we're trying to find position, we need to integrate again. X is equal to the integral of v with respect to t, and in fact I'll just write that here as well so you can see the various stages we're doing. So integrating, we've got 5 over 2 t squared on 2i minus t squared, so I'll just leave the half at the front, t squared on 2j times a half, plus some other vector. I'm going to call this vector d. Okay. Now we know initially that our particle is at this point, so that means that x is equal to 3i plus 2j when t equals 0. So using that knowledge, I'm just going to simplify this a bit first. So it's a bit easier to work with. And I'm going to just use that function on the next page. Oops, bring that up to here. So again, when t equals 0, x equals 3i plus 2j, that's its starting point. We can substitute t in here and substitute this x in, so we have 3i plus 2j equals 0, 0, it's d. So therefore, x equals 5t squared on 4i minus t squared on 4j plus 3i plus 2j, or if you want to, put all your i's together and all your j's together. So you've got 5t squared on 4 plus 3, all multiplying I, plus 2 take away t squared on 4, all multiplying j. So that's your position vector x, which describes where the particle is at any time t. So the position of the particle at time t we've done the acceleration. The last part here is the Cartesian equation of the path. Now remember that for Cartesian equations, our coefficient of I is x and our coef of j is y. Okay, so that's going to help us. We then need to take those coefficients and write y as a function of x. So first thing I know is that x equals 5t squared on 4 plus 3. I'm just going to rewrite that a little bit now. So multiply both sides by 4. 4x equals 5t squared plus 12. And so therefore we've got 5t squared equals 4x take 12. And I've got t squared equals 4x take 12 over 5. I'm doing that because I've identified, just looking at the next part, that I've got a t squared in it. So if I know what t squared is, I can straight up replace it. So I'm just going to move some things here, so I'm not going to have enough room. Let's move this up. Alright, so now what I want to do is look at y. So I know that y is equal to 2 minus t squared on 4. So I've got y equals 2 minus t squared on 4. And that's equal to, now because I know what t squared is, it's minus a quarter of t squared, and that's t squared here. So we've got y equals, everything here is going to end up being over 5, because I can do a bit of cancelling. So I know here that I could cancel the 4 and cancel that down to a 3. So I'm going to just rewrite the 2 as being 10 over 5, that's the 2. Minus, the 4's cancelling, so that's minus x on 5, and here the negative and the negative turns into a plus, and that's 3 over 5. So I've got 10 over 5 plus 3 over 5, so therefore we've got y equals 13 over 5 minus x over 5, and that is the Cartesian equation for the position or the motion of the particle. And you've done that by a few steps on the way to getting to this Cartesian equation. It's just a straight line, so ultimately this particle is just moving in a straight line with slope negative 1/5 and y-intercept 13 over 5. So what you've done is identified your forces, use those forces in F equals ma to find what the acceleration vector a is, integrated it to get velocity, used initial conditions to get that, integrated again to get your position vector, use the initial position to find the constant of or the vector of integration there, the d. And then once you have x, remembering the coefficient of I is x, the coefficient of j is y in a Cartesian sense, and then using those equations that you have then to express y purely in terms of x. And here just identifying that t squared is something that occurs in both, means that once you've solved x in terms of t squared, you can just substitute that straight in for your Cartesian equation.